Rate limiting is a critical component in any production system. It protects our backend services from being overwhelmed, it prevents abuse by bad actors, and it ensures fair resource allocation across all your traffic. Now let's talk about step one, which is clarifying the problem before we actually start designing anything. This is the most important steps in any system design interview. Jumping straight into architecture without understanding the requirements is a big red flag for interviewers. It signals that you might do the same thing on your real world projects, which is not ideal. Here are the questions we should be asking the interviewer. First, is this rate limiter for a single service or organization wide gateway? This fundamentally changes the scope and complexity. Second, what is the expected scale in terms of requests per second? Are we talking about thousands or millions of requests? Third, do we need to support multiple rate limiting strategies? Some systems need different algorithms for different use cases, so you should be asking this as well. Then we move to scope definition questions. For example, should the rate limiter be embedded in the application or deployed as a standalone service? Do we need real-time configuration updates without requiring a deployment? And what is the acceptable latency overhead for rate limit checks? Let's say if we add 50 milliseconds to every request, that might be pretty unacceptable in production scenarios. Finally, we clarify the constraints. What happens when the rate limiter itself becomes unavailable? Do we fail open and allow all traffic, or we fail closed and block everything? Do we need to support rate limiting strategies across multiple data centers? And what level of accuracy is acceptable for distributed rate limiting? The key insight is that these questions are not just for gathering information, they demonstrate to the interviewer that you think about edge cases and constraints before diving into solutions. Now let's move into step 2A, which is how we define our function requirements for the interview. Function requirements describe what the system should do from a user-facing perspective, and we should organize these into clear categories. The first category should be the core rate limiting behavior. FR1, which essentially stands for function requirement number 1, states that we should limit requests based on configurable thresholds per time window. For example, 100 requests per minute. FR2 states that we should support multiple rate limiting keys, including user ID, IP address, and API key. Different use cases require different identification strategies. FR3 states that we should return clear feedback when requests are throttled. Users need to know why their requests were rejected. The second category is rule configuration. FR4 states that we should allow different limits for different API endpoints. A search endpoint might have stricter limits than a profile view endpoint. FR5 states that we should support both hard rejection and soft degradation modes. Sometimes we would want to slow down the requests rather than completely block them. FR4 states that we should enable dynamic rule updates without requiring a service restart. Operations team need to adjust the limits in response to the traffic patterns. The third category is client communication. FR4 states that we should return HTTP 429 status code when the limit is exceeded. This is standard status code for rate limiting. FR8 states that we should include headers for remaining quota and reset time. Clients need this information to implement proper backoff. FR9 states that we should provide a retry after duration for throttle request. This tells clients exactly when exactly they can retry. Now let's talk about step 2B, which is defining our non-function requirements. Non-function requirements describe the system qualities, the characteristics that determine how well the system performs its functions. The first category is performance requirements. NFR1 states that we should have less than 1 millisecond latency overhead per request. Rate limiting should be nearly invisible to the user experience. NFR2, which is NFR just means non-function requirements. Number 2 states that we should be horizontally scalable to millions of requests per second. Our rate limiter should not become the bottleneck. NFR3 states that we should have a minimal memory footprint per track rate limit key. With millions of users, memory efficiency matters. The second category is reliability requirements. NFR4 states that we should be highly available with graceful degradation on failure. If the rate limiter fails, the system should still function. NFR5 states that we should have consistent behavior across distributed nodes. A user should not be able to bypass limits by hitting different servers. NFR6 states that we should have no single point of failure in the architecture. One component going down should not bring down the entire system. The third category here is operation requirements. NFR7 states that we should be observable with metrics for throttle requests and latency. We need visibility into how the rate limiter is performing. NFR8 states that we should have configurable alerting when the clients approach their limits. Proactive alerting prevents issues before they actually become incidents. NFR9 states that we should have audit logging for compliance and debugging. We need to be able to trace why a specific request was throttled. The key insight here is that non-functional requirements often drive architectural decisions more than the functional requirements. Latency requirements might force us to use in-memory storage. Scalability requirements might force us to use a distributed architecture. Now let's move to step 3a, which is traffic estimation. Capacity estimation is critical because it helps us understand the scale we are designing for and validates that our architecture can handle the load. It involves actually working with the interviewer to understand the exact capacity and traffic estimation, but for the sake of the interview, we have pulled example numbers here for both traffic and capacity. So for example, let's assume in this problem, the interviewer gives you 100 million daily active users for a large scale system. Then based on that, we can assume an average of 10 API requests per user per day. And we can assume peak traffic will be roughly 3 to 5x the average traffic. All these things you should be clarifying your interviewer as well. But if the interviewer tells you to assume these things, these are the safe numbers to assume with. Then we work on calculating the requests per second. If the daily request should be around roughly 100 million users times 10 requests, which equals to 1 billion requests per day, then the average RPS should be 1 billion divided by 86,400 seconds, which equals approximately to 11,000 requests per second. Peak RPS should be 11,500 times 5, which is equal to roughly around 58,000 requests per second. Then we consider the rate limit overhead. Each request requires one rate limit check. At peak, that means 58,000 rate limit evaluations per second. Our design target should be roughly around 100,000 requests per second to provide headroom for growth. You should always be designing for 2x your expected peak. The takeaway is that the numbers guide everything else. We now know that we need sub-millisecond checks at 100,000 operations per second. This rules out slow storage options like traditional databases and points us towards in-memory solutions like Redis. Now let's talk about step 3b, which is storage estimation. We need to understand how much memory our rate limiter will require to store all this traffic data. First, let's calculate the data stored per rate limit key. The key identifier should be about 64 bytes on average for compound keys like user ID plus endpoint. The counter value should be 8 bytes for the request count. The timestamp should be 8 bytes for Windows tracking. Total per key should be approximately 80 bytes. Next, we estimate the number of unique keys. If you are rate limiting by user ID alone, then we will have 100 million unique keys. If you are rate limiting per user plus endpoint and we have 10 endpoints, that becomes 1 billion keys. The strategy we choose significantly here impacts our storage requirements. Finally, we calculate the total storage. For user level limiting, 100 million keys times 80 bytes equals 80 gigabytes. For user plus endpoint limiting, which is 1 billion keys times 80 bytes equals to 80 GB. Redis can handle this in memory with clustering, though 80 gigabytes would require a multi-node cluster. The key insight is that the storage estimate helps us choose the right infrastructure. 8 gigabytes fits on a single Redis instance, whereas 80 gigabytes will require a Redis cluster. These are very different operational complexities. Now let's move into step 4, which is API design. A clean API design makes a rate limiter easy to integrate and maintain. We should define 3 categories of APIs. First is the rate limiter internal API. The main method should be check rate limit, which takes a key, a limit, and a window in seconds, and returns the rate limit result. The rate limit result should contain 3 fields: an allowed boolean indicating whether the request should proceed, a remaining count showing how many requests are left in the window, and a reset timestamp indicating when the window resets. This is a clean interface our application will be calling before processing each request. Second is the configuration API. We should have create rule, which takes a rule ID, key pattern, limit, windows in seconds, and action. We should have update rule, which takes a rule ID, new limit, and new window. And we should have a delete rule, which takes just rule ID. These allow operations teams to manage the rate limiting rules without having to do code deployments. Third is the monitoring API. We should have get usage, which returns the current count and window information for a specific key. We should have get top throttle keys, which essentially returns a list of the most throttle keys over a time range. And we should have get rate limit metrics, which returns the aggregate statistics. These support debugging and capacity planning. The takeaway is that a well-designed API separates concerns clearly. The check API is on the hot path, and that's why it should be fast. The configuration and monitoring APIs were not on the hot path, so they can be more feature rich and can be a little bit slower than the check API. Now let's talk about step 5, which is creating a high-level architecture. We need to understand the core components and how the request flows through the system. Our system should have three core components. First is the rate limit middleware, which intercepts the requests and performs limit checks. Second is the rules engine, which stores and evaluates rate limiting policies. And third is the counter storage, which maintains the current usage rate for all keys. The request flows works like this. Step A is extracting the rate limiting key from the request based on the user ID, IP, or API key. Step B is querying the rules engine for the applicable limits for this key and endpoint combination. Step C is checking the counter storage and updating it atomically. This must be atomic to prevent race conditions. Step D is either allowing the request and forwarding it to the backend or returning a 420 HTTP 429 response with appropriate headers. We should also consider deployment models. Option 1 is an embedded library within the application process. This has the lowest latency but requires updating every service. Option 2 is a sidecar proxy for language agnostic enforcements. This works well in Kubernetes environment. Option 3 is a centralized API gateway for organization-wide policies. This is the easiest to manage, but it does add a network hop. The key insight is that the choice of deployment model depends on your organization's needs. Embedded libraries are the fastest, centralized gateways are the easiest to manage. Most production systems generally use a hybrid approach. Now let's do a deep dive into rate limiting algorithms, starting with the token bucket algorithm. The token bucket is probably the most widely used rate limiting algorithm in production systems. Understanding how it works is pretty important. The core mechanism works like this. We have a bucket that holds tokens up to maximum capacity. Each request consumes one or more tokens from the bucket. Tokens refill at the fixed rate over time. If there are enough tokens, the request is allowed. If not, it's rejected. The token bucket has several important characteristics. It allows controlled bursts up to the bucket capacity. If the bucket holds 100 tokens and has been idle, a client can immediately make 100 requests. It provides smooth rate limiting with flexible burst handling. And it is also memory efficient, requiring only two values per bucket and the current token count and the last refill stamp. However, there are trade-offs to consider. The burst allowance can be undesirable for strict rate enforcement. If you need exactly 10 requests per second with no bursting, token bucket is not ideal. It requires careful tuning of bucket size and refill rate. These two parameters interact in non-obvious ways. Despite these trade-offs, it remains the most widely used algorithm in production systems because the burst allowance often matches the real-world usage patterns. The key takeaway is that the token bucket works well when we want to allow short bursts while maintaining a long-term average rate. This matches how most applications actually behave. Let's talk about the second algorithm, the leaky bucket algorithm. The leaky bucket is often confused with the token bucket, but it has fundamentally different behavior. The core mechanisms works like this. Requests enter a queue with a fixed capacity. The queue drains at a consistent rate limit regardless of the input. If the queue is full, overflow requests are dropped immediately. Think of it like water flowing into a bucket with a hole in the bottom. Water drains at a constant rate, and if you pour too fast, the bucket overflows. The leaky bucket has distinct characteristics. It enforces a strict and smooth outflow rate. No matter how bursty the input, the output is always constant. There is no burst allowance, which ensures consistent processing speed, and is often implemented with a FIFO, first in first out queue. The trade-offs are significant. Recent requests may wait while the old requests drain. If the queue is full of old requests, new requests have to wait or get dropped. This is not ideal when burst handling is acceptable, and it's actually better suited for traffic shaping than rate limiting. It's commonly used in network devices to smooth out the bursty traffic. The key insight is that leaky bucket is about smoothing the output, while token bucket is about limiting input without burst with the burst tolerance. You should choose leaky bucket when you need absolutely constant output rate, regardless of the input pattern. Now let's talk about the third algorithm, the fixed window counter. This is the simplest rate limiting algorithm, and understanding its limitations helps us appreciate why we need more sophisticated approaches. The core mechanism works like this. Time is divided into fixed windows, like each minute or each hour. A counter increments for each request within the current window. The counter resets when a new window begins. If the counter exceeds the limit, requests are rejected. The fixed window counter has appealing characteristics. It's extremely simple to implement and understand. It has a low memory footprint with just one counter per window, and it has fast lookups with O of 1 complexity. However, there is a significant trade-off. The boundary problem allows double the rate at window edges. A user can send n requests at each second 59 of minute 1, and then n more requests at the second 0 of minute 2. In a 2-second span, they have made 2n the request while technically staying within the limit in each window. This is acceptable for many use cases but can be exploited by sophisticated clients. The key takeaway is that fixed window counter is a good starting point for simple use cases. If your clients are well behaved and you do not need strict enforcement, this algorithm simplicity can be ideal here. But if you need to prevent boundary exploitation, consider the sliding window algorithms. Now let's talk about the fourth algorithm, the sliding window log. The algorithm provides perfect accuracy but at a significant cost. The core mechanism works like this. We store the timestamp of every request in a sorted log. When a new request comes in, we count all the requests within the sliding time window. We remove the expired timestamps that have fallen outside the window. If the count is under the limit, we allow the request and add the timestamp to the log. The sliding window log has excellent accuracy characteristics. It provides precise rate limiting with no boundary issues. We get an accurate count at any point in time, and there is no burst exploitation possible because we are always looking at the exact window. However, the trade-offs are pretty severe. There is high memory usage because we store every request timestamp. If a user makes 1000 requests per minute, we have to store 1000 timestamps. The cleanup and counting operations are expensive, requiring us to scan the log on every request. And this approach is not practical for high throughput systems at scale. The key insight is that sliding window log gives us the perfect accuracy but at O of n space complexity, where n is the number of requests. For high volume systems, this is pretty not ideal, and we need a way to approximate sliding window behavior without storing every timestamp. Now let's talk about the fifth and final algorithm, the sliding window counter. This algorithm provides the best balance between accuracy and efficiency, which is why it's actually widely used in the production. The core mechanism works like this. We combine the fixed window counters with the weighted calculation. We maintain counters for both the current window and the previous window. The weight is based on the overlap percentage with the sliding window. We calculate the weighted sum and compare it to the limit. Let me walk through an example. Say we have a 60-second window with a limit of 100 requests. The current time is 45 seconds into the current window, meaning we are 75% through. The previous window had 70 requests and the current window has 50 requests. The overlap with the previous window is 25%, so we calculate 70 times 0.25, which is equals to 17.5, and we add the full current window count of 50. The total is 67.5, which is under the limit of 100, so we allow the request. The sliding window counter has excellent characteristics. It approximates the sliding window with fixed window accuracy. It has low memory with only 2 counters per key, and it smooths out the boundary problem significantly. The trade-offs are minor. It is not perfectly precise, but is close enough for production use. It represents the industry standard compromise between accuracy and performance, and is used by major cloud providers for their API rate limiting. The key takeaway is that sliding window counter gives us the most of the accuracy benefit of the sliding window log with the efficiency of the fixed window counter. For most production systems, this is the right choice. Now let's talk about how to choose the right algorithm for a specific use case. We should choose token bucket when bursting is acceptable and expected behavior. If your users naturally have bursty traffic patterns, token bucket handles this gracefully. We should also choose it when different operations have different costs. Token bucket supports variable token cost per request, and we should choose it when user experience benefits from occasional spike allowance. Users appreciate being able to make a burst request after a period of inactivity. We should choose sliding window counter when strict enforcement without boundary exploits is required. If you cannot tolerate the 2x burst at window boundaries, sliding window counter eliminates this. We should also choose it because when the memory efficiency is critical for millions of keys. 2 counters per key is very efficient, and we should choose it with a simpler mental model is preferred for configuration. You configure requests per window, which is intuitive. We should choose fixed window when clients are well behaved and predictable. If you trust your clients not to exploit the boundary conditions, fixed window simplicity is attractive. We should also choose it when the simplest implementation is preferred. Fixed window is the easiest to implement if it's done correctly, and we should also choose it when the boundaries burst impact is acceptable. For many internal services, the occasional 2x burst is not a problem. The key insight is that the most production systems choose either the token bucket or sliding window counter. Token bucket for flexibility with the burst and sliding window counter for strict enforcement. Fixed window is for simple cases and leaky bucket is for traffic shaping rather than the rate limiting. Now let's talk about one of the hardest aspects of rate limiting, which is the distributed system challenges. The core problem is that multiple servers each have a partial view of the total traffic. If you have three servers and each maintains its own local counter, a client can hit all three servers and get three times the intended limit. Local counters alone allow n times the limit with n servers. This requires coordination or centralization for accuracy. We have several synchronization options. The first option is a centralized store like Redis for a single source of truth. All servers check and update the same counter. This is the most common production approach. The second option is sticky sessions that route the same client to the same server. This ensures that one server sees all of a client's traffic, but it has downsides for load balancing and failover. The third option is the eventual consistency with local counters and periodic sync. Each server maintains local counters and periodically syncs with a central store. This can temporarily exceed the limits but handles network partitions pretty gracefully. The trade off between consistency and performance is fundamental. Strong consistency adds latency on every request because we must wait for the central store. Relaxed consistency may temporarily exceed the limits but provide faster response times. We should choose based on how strict our limits must be. For abuse prevention, strong consistency is important. For cost management, eventual consistency might be acceptable. The key takeaway is that the distributed rate limiting is a classic consistency versus availability trade off. Most systems choose availability and accept some temporary limit overruns because a slightly exceeded rate limit is usually better than a failed request. Now let's talk about storage and infrastructure choices for a rate limiter. Redis is the primary choice for most production rate limiters. It offers in-memory speed with persistence options if needed. It has atomic operations with INCR and expired commands that prevents the rate conditions. And it has the native support for sliding window algorithms using sorted sets. We should also consider alternative approaches. Local in-memory storage works for single instance deployments or when approximately limiting is acceptable. It has zero network latency but no coordination across servers. Database counters work for low throughput systems only. They are too slow for high volume rate limiting but might be fine for daily quotas. Distributed caches like Memcache for atomic increment are also another option, though Redis is generally preferred for rate limiting because of its richer data structures. Failure handling is critical. Fail open means allowing requests when the rate limiter is unavailable. This prioritizes availability over production. Fail close means blocking requests when the rate limiter is unavailable. This is safer, but it does impact availability. We should decide based on whether abuse or downtime is worse for our specific use case. Most consumer facing services fail open because a few minutes of unlimited requests is better than a complete outage. The key insight is that Redis is the industry standard for rate limiting storage because it provides the right combination of speed, atomicity, and data structures. Unless you have specific reasons to choose something else, you should definitely start with Redis. Now let's talk about how to design rate limiting keys. First, we need to decide what to limit by. User ID or API key should be used for authenticated traffic. This is the most common approach for APIs with authentication. IP address should be used for anonymous or pre-auth requests like login endpoints that need protection before authentication. Endpoint or operative type should be used for resource-intensive calls. A search endpoint might need stricter limits than a simple read. Second, we need to choose the limit granularity. Per second limits work for real-world real-time APIs and high-frequency operations. Per minute or hour limits work for standard API quotas, which is what most public APIs use. Per day limits work for freemium tiers and billing cycles. Third, we need to consider the limit scope. Global limits across all endpoints provides overall protection. Per endpoint limits lets us set stricter limits on expensive operations like search or export. Composite limits combine multiple dimensions simultaneously. For example, 1000 requests per minute globally, but only 100 requests per minute to the search endpoint. The key takeaway is that key design should match our business requirements. A simple API might just need user ID plus endpoint. A sophisticated API might need multiple overlapping limits at different granularities. You should definitely start simple and add complexity only when it's needed. Now let's talk about how to communicate rate limiting decisions to clients. We should include standard response headers on every response, not just when limits are exceeded. X-rate-limit shows the maximum allowed request in the window. X-rate limit remaining shows how many requests are left in the current window. And X-rate limit reset shows when the window resets, usually as a Unix timestamp. These headers are let well-behaved clients stay under the limits proactively. When the limit is exceeded, we should return HTTP 429 too many requests status code. We should include a retry after a header with the number of seconds to wait before retrying. And we should provide a clear error message in the response body for debugging. Include the key that was limited and the current count if possible. Clients should also follow best practices when interacting with the rate limited APIs. They should implement exponential backup with jitter. When a request is rejected, wait 1 second, then 2 seconds, then 4 seconds with random jitter to prevent thundering hurt. They should actually respect the retry hyphen after headers when provided instead of using their own backoff. And they should monitor the rate limit headers to stay within under limits proactively rather than waiting for rejections. The key insight is that good rate limiting is a partnership between server and the client. The server provides clear information about limits and remaining quota. The client respects this information and backs off appropriately. This creates a better experience for everyone. Now let's talk about how to handle failures in our rate limiting system. When the rate limiter is unavailable, we face a critical decision. Fail open allows all traffic prioritizing availability. Fail close approach and blocks all requests prioritizing the protection. Our recommendation should be fail open for most consumer facing services. A few minutes of unlimited traffic is usually better than a complete outage. However, we should alert immediately when the rate limiter is degraded so the operation teams can respond or someone who is a DRI or on call. When the storage backend fails, we should fail back to local in-memory limiting temporarily. This provides appropriate rate limiting until the central store recovers. We should use a circuit breaker pattern to prevent cascading failures. If the Redis is down, do not keep hammering it with requests. And we should also auto recover when the storage becomes available. The circuit breaker should periodically test if the backend has recovered. Network partitions create additional challenges. For example, nodes may have inconsistent state temporarily, with different servers having different views of a client's usage. We should accept that some over or under limiting during partition. Perfection is not achievable during network issues, and we should design for eventual consistency, not strong consistency. Our system should converge to correct behavior once the partition heals. The key takeaway is that rate limiting should never be a single point of failure. The system should continue to function, perhaps with reduced accuracy, even when the rate limiting infrastructure has problems. Now let's talk about monitoring and observability for our rate limiter. We should track several key metrics. First is the counter request allowed versus throttle, broken down by endpoint and key. This tells us how much limiting is actually happening. Second is the rate limiter check latency at P50, P95, and P99 percentiles. If the latency increases, something is wrong with the storage layer. Third is the current usage as a percentage or limit per key. This helps us identify clients approaching their limits before they start getting throttled. Our alerting strategy should include multiple triggers. We should alert when the throttle rate exceeds the normal baseline. A sudden spike in throttle requests might indicate an attack or misconfigured client. We should alert when the rate limiter latency degrades. This could indicate Redis problems or network issues, and we should proactively alert when the client approaches their limits. This lets us reach out to high volume clients before they have problems. For debugging support, we should log throttle requests with the key, endpoint, and current count. This helps us investigate why specific requests were throttled, and we should also provide an admin API to query the current state of specific keys. Operation teams need to look up whether the specific user is being throttled or not, and we should build a dashboard showing top throttle clients over time. This will help identify systematic issues and inform the capacity planning. The key insight is that the rate limiter without observability is a black box. When something goes wrong, you need to have visibility into what is being throttled and why. You should be building monitoring from the start, not as an afterthought. Finally, let's wrap up with some tips on how to structure your answer in the interview and handle common follow-up questions. For structuring your answer, always start with clarifying questions when designing. Interviewers want to see that you gather requirements first, state your assumptions explicitly when the interviewer does not answer or says it's up to you. And you should walk through the framework steps in the order before starting the problem. This shows that you have organized thinking and a planning that you aim to follow. You should prepare for common follow-up questions as well. The first could be that how would you handle rate limiting across multiple data centers? The answer involves geo-aware routing and either local limits per region or a global coordination layer. The second is that what if Redis becomes a bottleneck? The answer involves Redis clustering sharded by the key or a hybrid approach with the local caching. The third is how would you implement rate limiting for GraphQL with variable query cost? The answer involves cost-based rate limiting where complex queries consume more quota. For demonstrating seniority in interviews, you should be discussing trade offs for every design decision. There is no perfect solutions, only trade offs. You should mention operational concerns proactively before the interviewer asks. Things like monitoring, alerting, and deployment should come up naturally. And connect the technical choices to business requirements. Explain why we chose a token bucket, for example, because our users have bursty traffic patterns. The key takeaway for your interviewer is this, that the rate limiting is a well understood problem with established patterns. Your job is to not invent something new here. Your job is to demonstrate structural thinking, discuss trade offs with the interviewer, and show that you consider the operational concerns.